All right. Well, thanks everybody. My name is Luke Zoet. I'm a professor at Wisconsin. I work on glacial processes sometimes. Things I work on a lot of the time are focused on sort of glacial dynamics and processes at the ice bed interface. This is probably gonna be a little bit different of a talk than what we've heard so far, simply because I'm not going to talk about anything that we did there. Talk about stuff that we're proposing to do and stuff we're planning to do. We have worked up there. We did a field season last year with Dougal. Dougal led it. There was a big geophysics campaign, 100 seismometers, lots of GPS, active, passive seismics, all sorts of other instruments that we put out. And he's going to talk about all that. I'm not going to talk about any of that. And so what I'm going to talk about is part of the proposed plan that's coming up dealing with the potential to drill to the bed of Taku and try to put some instruments down there, and at the same time look at measurements that we'll make at the surface. So in the background here, I have this really cool mosaic called Terminus, made by an artist called Terry Nichols. And what they did was, cut out all these little tiles and place them in a pattern to sort of resemble the shape that you're seeing here. And I think this has some analogs for what we should be thinking about when we think about subglacial processes, hydrology, inglacial processes, all these things, all these different aspects of how glaciers work. Um, so this is some cool photos. I don't know how many of y'all get all the way down to the terminus, but this is last year when we flew in there. I came up over the ridge, and so we had some nice, interesting helicopter photos. And so you can see this big calving event that's showing up here in the frame that where we had this big calving episode. We could see that at our camp from time to time. We'd see, the river was basically ice free, and then you come back later and there'll be huge amounts of icebergs floating in it because overnight there was some large calving that had occurred. And so here's just another shot of it looking back over this region. And you can see this area is pretty heavily crevassed. You can make your way through it, but it's not necessarily easy, or you can't take a super straight line to move through this area, which impacted some of our planning for last year in particular. A lot of times I like to start with this really simple diagram from Nye. In some ways, I think this is kind of the birth of glaciology when he sort of put these mechanics together. What he did here was he was looking at essentially a simple diagram of a glacier from the side. So this would be the surface of the ice, and this would be the bed, right? And this would be as if you drilled a borehole through the ice, and you came back some time later and you look at the borehole and it has a deflection like this. And what Nye reasonably worked out was from a lot of glaciers where they had sort of observations of how much they had moved at the surface over some period of time. And they knew something about the deformation or the flow law of ice. He worked out that a lot of the forward motion that you observed at the surface wasn't all coming from deformation of the ice, and that there had to be some other component at the bottom where the glacier was slipping over the bed. And so a lot of times we hear this analogy of glaciers like honey that's oozing down a table. A better analogy is that you have an ice cube on a board and you tilt the board a little bit, and the ice cube slides down the board. And right where the ice cube sits on the board, there's all these complex frictional reactions that are essentially regulating how fast the ice moves. And so trying to understand what's going on at the bottom while challenging is particularly important for glacier dynamics. What glaciologists didn't realize at this point, glacial geologists had known this for 100 years by this point, but the two communities didn't talk to each other, was that the beds of these glaciers are often made up of sediment. And Lynn motivated this nicely in her talk and talked about like the different sides of the lobes and how they're behaving very differently. And that has to do with sort of complex interactions between the hydrology and the bed and the topography and all these slip facilitating mechanisms. And that are playing out in particular, Taku Glacier. It's really, it is a world-class site to go to try to study these dynamic processes. It's beneficial that JERP is located there because it's a great glacier to study if you're trying to understand dynamics in particular. So what we do a lot of the time to try to simplify this in a way where we don't have to worry about all the complexities that you might see in the field at a place like Taku is we use machines, right? This is a machine called a cryo ring shear device that we built at UW-Madison. And effectively what it can do is spin a donut of ice inside of the sample chamber over some base. And the base can be comprised of sediment. It can be comprised of rigid rocks. We can take sediment from specific glaciers if we think the sedimentological and hydrologic properties of the subglacial till or subglacial sediments beneath the glacier are effectively regulating the dynamics and put them in here. We can do all sorts of simplified tests. And the point of this isn't necessarily to replicate all the complexity of nature. It's to simplify the system to the basic physics and understand the basic fundamental physics that are driving the processes that we see, that are all convolved together. And we see at the large scale as sort of perturbations in velocity, perturbations in subglacial hydrology. But you can't really work your way up to the complexity of a full glacier and make good prognostic predictions without understanding the base mechanics of what glaciology is based on. And so that's kind of what we do with these machines, is try to understand those. Here's another example of this. So here inside of this sample chamber right here, like I said, is a ring of ice, and it's in this diagram here, it's placed on top of till. And so the ice would be spun atop the till. And the sample chamber is transparent, so we can look into it and see what's deforming and how it's occurring during the processes. We can look at the bed and watch how the bed is specifically deforming in response to the ice ring being driven atop it at a prescribed rate. We can instrument it. We can instrument anything we want. We can put seismometers in there. We can put electromagnetic sensors in there, measure the radar properties of the ice bed interface. We can measure water pressure. We can measure the resistance to sliding, measure temperature everywhere. So we can really perturb the system in interesting ways that get closer and closer to what occurs in reality, but without necessarily all the complexity in reality that can make the signals hard to interpret. Here's just sort of a cartoon of what I mean by this. So in this case, the ice would be sliding over the bed, and the bed is there's slip at the bottom. Slip is what the term we use a lot of times instead of sliding. Sliding, it indicates right at the interface. Slip would indicate sliding at the interface and some component of deformation of the sediment below. And you can have, for example, clasts that might be embedded at the ice bed interface that, as they're flowing along, are mobilizing the sediment in the bed, and that's resulting in a difference in the slip law, the way that you parameterize how fast the glacier slides in response to the applied gravitational driving stress of the system. And so here's a sped up view of one of these pictures. And so this is like 2.5 centimeters, and it's spread up about 3,000 fold. The ice is moving from left to right, and you can see that sediment's being mobilized at the bottom, and that if you look and you go deeper and deeper into the sediment column, you see that deformation decays with depth. And so this gives us a good idea of how sediment's being moved, what the physical processes are that are governing slip at the bottom of the glacier, how water pressure and hydrology feeds back into the system. Here's another example of growing like this frozen fringe. You have this debris laden ice at the bottom, and you can see that some of the material is basically adhered to the overriding ice. It's a very effective mechanism for moving sediment around, and it's also changes the friction at the ice bed interface in a different way than if you didn't have this sediment adhered into the ice. When we do these things, a lot of the times what we're trying to do is relate essentially the sliding speed, or you can think of in that example of the ring shear, how fast the ring is spinning, to the frictional resistance, how hard it is to spin it. And that's the basis of the sliding law. So in this example of a paper by Doodle Hansen, as the sliding speed goes up from left to right, the resistance goes up too until it meets this dotted line. And that dotted line is simply the Coulomb strength of the till. And you can think of the subglacial interface as a series of like links in a chain, and it's going to fail at whatever the weakest link is. So at these lower speeds, what's happening is the sediment is failing at a point that is below the Coulomb strength of the till. And then once you hit this certain velocity, the system is essentially regulated by the Coulomb strength of the till. And the mechanics of this are in the paper, and the benefit of the ring shear is we can not only get the results like this, we can go back and investigate the physical processes that will give rise to these types of this type of slip law that allows us to make accurate predictions in things like ice sheet models and glacial flow models and things like that, and get away from just imparting tuning variables and other non-physically based processes that are a lot of the times used in prescribing how glaciers move. Okay, click the wrong way. We can do that also with hard beds, right? So here's a hard bed. In this case, we put debris in it to understand how debris in the basal ice alters the drag response as you slide over, in this case, marble steps that are imposed in the bed, right? We can investigate the processes of that, right? How do these debris that's in the basal ice press into the bedrock, and how does that change as a function of things like the vertical flow speed? How does it change as a function of things like water pressure at the ice bed interface? How does it change as a function of the horizontal flow speed? And all these things manifest themselves in some sort of drag response that is incorporated into a slip law. And so here's just sort of four end members of types of cases that we've looked at. I won't go into the mechanics of this. I'm just sort of telling you this is a setup for the rest of the stuff. If you're interested in the various processes, there's an IGS talk that I recorded like 2 weeks ago that's up online that you can see all the details of it. But the point of this is that on these small scales, we kind of understand the physics of subglacial slip fairly well, right? At this point, I would say. I mean, it's an adage that's put in papers all the time. We don't understand sliding or slip very well. I would say that that's becoming less and less true. Like, I think that in many instances, we do understand subglacial slip pretty well, the physical processes. The hydrology, that's probably a different problem to some extent. That's complicated, and we're still working on those types of things. But the actual mechanics, we kind of understand. Now, when we do that, we find that in many instances, we get this similar type of slip law that as the sliding speed goes up, the basal resistance initially goes up, and then it sort of rolls over, and we get this thing called a regularized cooling. And we've seen this for a number of different bed types, like I showed. Some of them are a little bit different. For example, when we have hard bed with debris in it, we had this extra rate strengthening component that's helped stabilize numeric models in the glaciers themselves. But like I showed there, those are just snapshots, right? What we're doing in the ring shear is basically simulating one small piece of the bed, right? All the care we've taken to build this machine and the way to operate it, it's not like it's representing the entire bed of the glacier. It's representing one element of the bed. And in some instances, you can extrapolate from that one element of the bed up to larger scales, like for example, when there's sediment in the bottom of the ring shear. But other instances where there's not sediment, where there's hard beds, you need to use process-based finite element modeling like Elmer Ice to be able to scale from the ring shear to the real conditions. So if I go back to this mosaic, what I would say is when we think about a glacier bed, it's kind of like this mosaic, right? What we should be thinking about is that different pieces of the bed are probably responding in different ways. And that if you convolve all those different pieces together and all those different responses together, you'll get some bulk frictional response for some portion of the bed that depends on the individual constituents of what they're made up of. So something like this, maybe this tile, if we're looking down at this mosaic and we picture this thing as the bed of a glacier, maybe this tile behaves with these types of mechanics, and this tile behaves with these type of mechanics, and this tile behaves with these type of mechanics. This tile behaves with these type of mechanics. But it's not like they can all operate independent of each other. It's a viscoelastic block of ice that's on top of it that's transferring stress from one part of the bed to the other. And the way that we have to think about it is that we have to kind of understand what are these different elements of the bed, where they might exist, and how they respond. And if we get that right, we should be able to make pretty good predictions of how the bulk of the glacier is moving, why the glacier is moving, how it's moving, what it responds to, and things like that. And we don't have to get everything right, but we probably want to get some key points of it right. And we probably want to have some idea of understanding where it might vary in properties from one spot, like on this iceberg, to up here to the sky to the bed at the bottom, right? So we need a way to determine the basal properties at these different scales, right? When we look at it from the surface, that's basically an integration of a big part of the bed. The ice is essentially a low pass filter that's taking in some components of the bed, convolving them together, and then you see them at the surface. The same way an ice sheet model discretizes sections of the bed that might be smaller than an ice thickness in some instances. But when you look at the surface response, you're sort of integrating more and more area, the thicker and thicker the ice is, essentially. And so one way that people have done this is to drill through the bed and install things at the base of glaciers. And the classic tool that's used in glaciology is something like this, a plow meter. For those of you that haven't seen it, you've essentially drill a hole through a glacier all the way to the ice bed interface, and then you drop this rod down and you hammer it into the underlying sediment. And then as the ice flows from left to right, It essentially bends the rod, right? It puts a torque on the rod that causes it to bend in some way. Now the rod has been instrumented with lots of little strain gauges, and those strain gauges tell you how much the rod is bending. And so what you do is before you hammer this thing into the earth, you basically calibrate it in a lab. You say if it bends this much, how much force is on it? If you bend this much, how much force is on it? If you bend this much, how much force is on it? And that allows you to take the measurements from the field and reconstruct how much force is being delivered in particular to, this part of the rod as the ice drags this thing through the underlying sediment. You get measurements like this. So this is force, right? This is the resistance, or this is essentially how much bending motion has gone into that bar for one of these plow meters. There's an azimuth here, so you kind of know which way it's tipping and which way it's moving. There's another one of these force sensors, and then in this case, they put a water pressure sensor in the borehole that goes up and down diurnally as the water pressure goes up and down because of lots of melt during the day and less melt during the night period. And so a lot of this work was pioneered by Urs Fischer in the late 90s. And this this is not easy, right? It's not easy because the fact is, how do you go from force of this thing bending, for example, to the properties we actually want to know? Basal shear stress, subglacial water pressure, um, normal stress, how consolidated the tills are. All these things are sort of complicated, and you need to come up with your own methods essentially to go from what the instrument can give you to the things that we actually want, the physical quantities that we actually want. And Urs did a great job building these types of analogies to sort of go from what you measure to the types of properties that we are needed essentially. Meters, they're a great source of information, right? They tell you a lot of information about the bed. They provide details about the bed strength, but it's essentially integrated over the length of the rod, right? So you don't know if the upper part of the till is stronger than the lower part of the till because all that force is exerted throughout the rod at different spots. And so it can be hard in some respects if the till or the subglacial sediment is heterogeneous to know is this associated with one component of the till or one section of the till, or is this a representative like the full length of the till that's being penetrated? The other thing is when you drill that borehole to the bed, you've hydrologically connected the subglacial hydrology to your borehole, right? And maybe that changes the hydrology in a way that's different from what it would be if you didn't drill that borehole to the bed. It can be taken into account. It's better if you can drill multiple holes, you can get an idea of like the component of it, but it's something that needs to be considered. And like I said, it's challenging to go from these measurements to the physical values that are desired to help constrain these subglacial processes like slip and hydrology. Now, the thing that's to me a little interesting is that in the field of glaciology, where these types of plow meters and other meters that are similar to it have been used, we've effectively invented these. These aren't necessarily a tool that's widely used in any other field. They're kind of a glacier specific thing, right? However, there are other tools that are much more widely used that can give you these type of properties and more that have standards and things like that. And so what I'm advocating for, I guess we're advocating for, is some other possibility. Can we build a different type of tool that'll give us the things that we really want to know about the bed in in a way that utilizes standards from other fields, in particular civil engineering, right? Civil engineers have cared a lot about these exact same properties that we care about, and they've developed techniques to measure them, and they've been widely employed all over. Glaciology has largely chosen not to follow the immense amount of work that civil engineers have already put into this, but that doesn't have to be the case. We could just start adopting what they're doing. And so one example of this, and one that I think is useful, is something called a cone penetration test. Every time you go out and you're building there, you all sitting at Maine, before they did that, they ran some test like this to assess the consolidation state and the shear properties of the sediment before they built the structure. And what this is in this case is it's essentially there's a giant back force here, and there's a hydraulic pushing rod that pushes the steel rod into the ground, and at the end of it is a cone that has a certain angle. And what you're doing is measuring how much force you have to push on this rod to shove it through the medium, right? And then you pull it back out. The reason that this is useful is the cone penetration test has a standard, right? Unlike the plow meter, where ERS had put all this work into figuring out what it actually means to go from one plow rod that he built to the measurements we want. Uh, we wouldn't have to do that if we used these penetration tests. You know, every civil engineering class, every soil mechanics class, every civil engineering student knows these, right? They know these standards, they know how to apply them, they know what they mean. These things have been used tons and tons of times. And so if we were to employ an instrument that was like a cone penetrometer, we could utilize the decades of work that civil engineers have done in interpreting the results to give us exactly what we want, right? We don't have to reinvent the wheel. But it's challenging, right? We have to invent the tool, right? We have to invent a tool that would work in our environment, but would give us results similar to what they derive from just pushing it through the land, essentially. And so just to zoom in a little more, the tip of these things look like this, right? So essentially at the end of it, you have essentially three components. You have a friction sleeve, a pore pressure sensor, and the cone right here. And the cone has a very specific angle to it, right? That angle is very closely tied to the theory. And so the geometry of the cone is really important for interpreting the measurements that you make of how much force you had to apply to this to push it through the sediment to convert that to things like shear stress. The pore pressure sensor here tells you something about the in situ pore pressure of the medium you're pushing through. In the friction sleeve here, you can think of it as if this is in the dirt and this instrument's being pushed down, the dirt on the side is rubbing on it and that creates friction. And this system can measure the friction angle of the sediment as it's pushing through it. And using these three different types of measurements, you can get out a multitude of information that is useful for parameterizing and estimating subglacial slip. So for example, things that are measured, like I said, are the tip resistance, the sleeve friction, and the pore water pressure. Also, importantly, you can measure the pore water pressure dissipation, right? So imagine you take some sediment and you ram that cone through it. Initially, what happens is the pore space gets squeezed. That causes the water to diffuse out of it. And if you can measure how quickly the water diffuses out of that area that you're squeezing, you then know the hydraulic properties, the hydraulic conductivity or the permeability of the sediment. Another thing that's useful. So with this cone penetration theory, it allows you to estimate things like soil density, shear strength of the sediment. This is a big one. Water pressure, the hydraulic properties. And you can do things like soil classification, stratification, and estimates of the geotechnical properties of the subglacial sediment. All things that are needed to get accurate representation of how glaciers will respond to some perturbation to the system. It allows the other thing that this can do is if you build a cone penetrometer in a specific way, you can actually hydrologically isolate the borehole from the subglacial system. And so it alleviates the problem that we have with most of these borehole measurements where the connectedness then can in some ways pollute or can make the signal hard to interpret. You can essentially stop the water in the borehole from communicating with the water at the bed. So here's a diagram of the one that we proposed to build. I won't go into all the mechanics of it, but we've got it pretty much specified. But essentially, the components of it are there's a needle or a cone inside of this hydraulic pneumatic actuator here that gets inserted into the till, right? And then it retrieves it and the glacier slides and it does it again. And it does it again. And so by just using the natural motion of the glacier, you could repeatedly probe the bed and measure the resistance to the needle being inserted to the till. And you could figure out all the sedimentological and hydrologic properties you want, not just integrated over the whole load cell, but because you know how far the needle or the cone is into the till at all locations as you go deeper and deeper into the till. Now, you need something to push back against, right? And in a normal situation, what they have is a giant solid drill stem that goes back all the way up to the surface. And while in theory you could do that, that would be hard to do in a glacial setting. And so the way that we propose to do it is use a packer. And what you can think of this is it's a hydraulic bladder that expands and essentially would couple the whole CPT to the sides of the borehole to provide the backstress that could push against and then insert the needle into the till. Yeah, so you could that in that way that would also isolate the borehole hydrologically from the bed. So the plan is we're already sort of partway through this. Last summer we went up there and put out 100 seismometers all over the glacier. We left a bunch of GPS up there. Um, we plan to go up this summer and with Jerp's help use the drill to drill to the bed. This was the original plan. We might modify it a little bit and just drill over on this side of the bed and deploy a plow sensor that Dougal's having commissioned by John Lehman's company at the bed at the ice pit interface. In theory, we have a grant that's been pending at NSF now, which I'm sure many of you have, for over a year that was, I think, within a few days of getting funded a year ago to build this CPT along with expand this geophysical survey and go back out and install this instrumentation. So we have the plans. We know how to build it at this point. We're just waiting to see if the project will be funded. And so when you think of this mosaic, think of like if we know these different bed segments from the active source seismics and the radar and the passive seismics, they would make excellent drilling targets, at which point we could deploy these downhole tools like plow meters and these cone penetrometers, and we could figure out the properties here and see if they relate to what we have in the lab. We could figure out the properties here and relate them to the lab, and so on and so forth. And that's a way to connect the mechanics that we can study in the labs to the in situ field. And then if you co-locate all of these cone penetrometer tests with arrays of passive seismometers at the surface, you can see what the surface expression is of these subglacial regimes, essentially, that are behaving mechanically different. Um, Here's Dougal. He's installing a seismometer. He'll talk about this. This is a tool we built to couple the seismometers in the ablation zone that seems to significantly improve the signal to noise ratio in these areas. But Lynn showed some pictures like this too. This is the front of the glacier. And the reason I'm showing this is if you look at this, there's all sorts of sediment out here. A lot of it's outwash, some of it's till that's in these moraines. It's a little hard to tell. But what you can do also is you can scoop up sediment from these areas and you can bring it back to the lab and put it in the ring shear and constrain the subglacial aspects of Taku that you measure in the field with the types that you measure specifically in the lab. So here's an example. Here's a seismometer we put out to measure water flow in the stream. It almost fell in the water. We got about a day before it did. But you can scoop up this type of sediment and put it in the ring shear. And then you can build a cone penetrometer in the ring shear and you can compare it to what you do in the field. And that allows you to directly map the processes in the field to what you can do in the lab where you can more exactly control sort of what you're measuring. So this is a picture from last year. This is Gabe, which I like this picture because if you notice, there's these two moose back here that are giving him a bad time, but he doesn't really seem to care. So he was a good-natured guy. Okay, I'll stop there and take any questions that anybody has. Or not, we can go next on for our time.
All right, thanks, Luke. Any questions from the room or online? I have one, Luke. How do you account for the fact that the glacier ice will be deforming too, like as you're moving along to take your core samples?
Yeah, that's a good question. So it probably what the tool's not so big that the deformation will destroy it, but it will make it difficult to get it out. And so if we got 50% retrieval of these devices, I would be impressed. I think a lot of them are going to get jammed at the bottom and be hard to pull back out, would be my guess, because of the ice deformation. So I think the data will be good, but we may not be able to get the instruments back.
Thanks.
Great talk, Luke. Seth here. Good to see you. I guess my question is not about any of the science. It's more about having you guys think about how else Germ can start to support you guys if we think about the ice field as a long-term study site over multiple years. Things that we've been tossing around. We've submitted congressional land requests to install new field stations, for example. So one of the high ice divide, Northwest Branch, we're proposing to put kind of a field station down towards the terminus that could still access the ice as well. So things like that came to mind, but we were trying to come up with other things that might be of value from a community resource perspective. So, if you have any thoughts now, or if you want to think on it, of course, as well.
Yeah, I mean, I think what I would say, one thing that would be useful, Seth, is every time that you run that drill, if you go to the bottom and you get at least a handful of sediment,
Yep.
that would be extremely useful because we don't need if we just have a little bit of sediment, we can do all our tricks, right? We can measure the grain size distribution, we can measure the lithology of them. And then all we do is we drive around Wisconsin and pick up tills and mix them together until we have that same composition as you have at Taku because we have such a range of tills here, and then we can use them in the lab. But if we don't have any, if we don't have any sediment, then we can't do that, right? And we're in the hydraulic permeability varies over like 6 orders of magnitude. So without that, it's really hard to constrain, in particular, the subglacial hydrology. And if you can't constrain the subglacial hydrology, it's really hard to then go back to understanding subglacial slip and sliding.
Cool. All right, well, like fortunately you got Jake with you this year and Jess probably helping out. So you got a few people here that are gonna be working with you.
Yeah.
Maybe that's an effort that we can make sure it goes into it as a collaborative effort moving forward.
Jake here, I'm the drill guy. So we just ordered last week, we just put in an order for a sediment collector device that I had designed specifically for boreholes. So it'd be low profile and percussion hammer style. So hoping to get sediment samples from each borehole we drill. Should be able to take 2 meter samples. If it'll actually penetrate that far, we'll see.
That would be amazing. Yeah, Dougal told me that you were working on trying to get a sediment collector, and I mean a 2 meter sample would be amazing. You could even study the stratigraphy in it with something like that. But even if you got 300 cc's of it or something, that would be a game changer too, I think. Because I'm not totally sure that that sediment that's in front of the glacier is 100% reflective of what's underneath it because like Lynn was talking about, it's been washed it's been washed by proglacial streams and then overridden and things like that. And so is it what's underneath it? I don't know. Yeah.
That was my thought as well.
Well, just for your knowledge, look, so these guys will be helping you guys down there this year. But then of course, after they're coming up to Camp 10 to punch to Swiss cheese the valleys on either side of Camp 10 this year is a goal. So hoping to get 4 to 8 more holes. Who knows how many kind of further up glacier as well. But Brad Markle and I have keen plans to make sure this drill is used consistently on a yearly basis if possible. So that's a good target for us.
Yeah, that sounds amazing.
Great. Thanks, Luke.
Thank you.